This takes us to problem number 9. All right, the last problem I'm going to show you. Okay, problem 9, a student builds and calibrates an accelerometer, which she uses to determine the speed of her car around a certain unbanked highway curve. So unbanked, when you bank it, that's when you make it sloped, the ground. You'll see that on on-ramps and off-ramps from highways, or like on a racetrack, right? They'll like bank the curve around it, right? Anyway, point is, unbanked highway curve, it's just flat. Banked curves are going to pop up later on in this problem set here on problems 12. See, it's banked at 15-degree angle, right? Or 13, 14. Okay, anyway, getting back to this. Builds and calibrates an accelerometer, which she uses to determine the speed of her car around a certain unbanked highway curve. The accelerometer is a plumb bob with a protractor that she attaches to the roof of her car. A friend riding in the car with her observes the plumb bob hangs at an angle 15 degrees from the vertical, and the car has a speed of 23 meters per second. What is this dribble acceleration of the car rounding the curve? So you say, oh my gosh, how is that going to work? All right. Here is what we're going to do. We're going to take a protractor, right? A protractor. A protractor. And I'm going to have this hanging, okay? Now, I'm going to attach this to the roof of the car, all right? Now, imagine what would happen if we accelerated that way. If we accelerate to the left, right, what would happen to this, like this weight hanging down there? Right now, it's hanging at, 0 degrees deviation from vertical. But if I accelerate to the left, right, this will accelerate, and this will end up. Now, did this swing back? No. This and the car attached to it accelerates this way. Do you see what I'm saying? It's like trying to leave this behind. All right. Now, if we're accelerating along, this is going to be hanging at some angle, hopefully. Okay. If we had a constant acceleration, eventually it would start to swing a little bit, but it would eventually settle out and be at this one angle as we accelerate along with a nice smooth acceleration. So it's going to look like, in this case, it's supposed to swing to 15 degrees, 15, like that. Okay. As we accelerate along that way. Does that make sense, kind of? Okay. And you say, now what's going on there? If I draw my little Excel, so here's like, that's the roof of the car, right? Okay, and here's my my protractor, right? Whoops. Anyway, and it's marked off, gradated off. Right, good, got it, right? Okay, and you say, hey, if I'm accelerating to the left, the pendulum bob is going to end up at an angle over here somewhere. Okay. All right. And you say, well, why does that have to happen? Okay. Forces on the pendulum bob. There would be gravitational force. Oh, I'm doing my forces in purple this time. And then there's going to be a tension force, right? That's unfortunate. A tension force along that string. You say, no, I need this to be back at an angle. Why? Because I need to have a force to accelerate this thing forward with the car, right? That's going to be this component of the tension. This part going to balance out gravity, right? If I call this angle with the vertical theta, then this is t cosine theta, right? This is going to be t sine theta. And I can see this t cosine theta is going to balance out gravity, right? Because we're not accelerating up and down. The car is not accelerating vertically, right? But if we accelerate that way, this is going to be at this angle back like that, okay? Because the car takes off ahead, right? And this guy's getting tugged along behind, and this horizontal part is what accelerates it. Okay, so we've got that. Now what we're going to do, so yes, and so I know that this t sine theta is what's going to accelerate it. I feel like I should show you that real quick. I'm going to show you that real quick. and then we're going to talk about applying it to this problem. But if I do the most important formula in physics, I'm going to do it twice. Once for each axis, okay? If I do this for, I'm going to call this the horizontal axis, okay? I'm going to call this the z-axis, all right? Is this accelerating in the z-axis? No, right? And so this is just going to be, again, choosing to call z and x, and I call this positive. Then you say, hey, this is going to be t cosine theta minus mg equals 0. And so I can get that the tension is mg over cosine theta. Coming over here, doing this horizontal axis, I'm going to have that t sine theta equals mass times that acceleration, and we are accelerating this way. And so you can see if I substitute this in there, look at the coolness that's about to happen. See those masses? What masses? Didn't need to know the mass of the pendulum, Bob. Hey, sine over cosine, you know what that is? We get that g tan theta is the acceleration. And theta, you just read right off there, and boop, g tan theta, 9.8 times tan of that angle, bam, you have your acceleration. Isn't that cool? Right? So you can use something like this as an accelerometer, right? You just read off the angle that this is at, and you know how fast you're accelerating that way. Cool, huh? So I could hang this, so if I'm driving this way, I could hang this from the roof of my car, and when I accelerate forward, this doesn't actually swing back, right? The car goes forward, really, right? You know what I'm saying? And then tugs this along, right? And the faster I accelerate, the bigger angle I would get, the slower the acceleration, the smaller the angle I would get. Going constant speed would just be hanging vertically. Neat. Neat, neat, neat. Now, in reality, of course, if I accelerate up, this is going to swing and it'll overshoot the final point. It'll kind of wiggle around a little bit until it comes to rest. And a little friction would be helpful there. But that's the idea. We used to do something like this when we went to on trips to Great America back in the day. Except instead of having this pendulum bob get blown around by wind, instead we had a little tube, a little plastic tube, right, with plugs, and we put a little ball bearing in it, and the ball bearing would roll to the angle instead. Okay, neat. Okay, and the physics is the same. Instead of tension, it's a normal force from the bottom of the tube on the ball. But yeah, but a component there forward, pushing it forward. Anyway, neat. Okay, but what I'm going to do now, okay, for this problem, all right, that they want here, right, what we're going to do is we're not looking at setting up this accelerometer like this, driving forward and have it like this. Instead, we're going to set it up across the car. You're like, really? Here's why. Let's say that we are negotiating a left turn. Here is our car, right? Okay, there we go, right? And we are cruising along this way. It's a top-down view, right? I'm making a left turn, yeah? I am going to put my accelerometer crossways on the ceiling, like this. There's the accelerometer, okay? And that pendulum bob will end up at an angle like this, okay? If I were to turn, wouldn't this thing, it'll look like it's swinging out. It's not, it's trying to keep going straight, but I am turning left, right? And I am moving left, right? You know what I mean? And it ends up kind of looks like it's swinging outward as you go around a circle. You know what I'm talking about, right? Okay. You say, of course I do. Of course I do. I know what you're talking about. Oh, I'm upside down here. Well, you know, life's like that. And you say, hey, I know that if I were to walk around in a circle, it would look like it is swinging outward, wouldn't it? You know what I'm saying? I hope you can see this. But you get it, right? Okay. And so, coming back down here, you would say, you say, yeah, I get it. It's going to be, this is going to go towards the outside of the circle. It's going to look like my acceleration is to the left. My acceleration is inward here. centripetal acceleration, and I can measure that centripetal acceleration by this exact same calculation. Except now, this is not x. This is actually the radial direction toward the center of the circle, isn't it? This is the radial, and so this is the centripetal acceleration. All right, and that is the way this is going to work. We are trying to find the centripetal acceleration when rounding the curve. We know g, we know the angle is 15 degrees in this problem, and so you say, hey, 9.8 times the tangent of 15 degrees, doomby doomby doomby, and I get 2.6259. Let's just call that 2.63 meters per second squared is my centripetal acceleration. That is the answer to part A. Okay? Part B says, all right, what's the radius of the curve? You say, well, the centripetal acceleration, isn't that going to be equal to v squared over r, right? And so that means to find the radius of the curve, I'll just rearrange this. It'll be v squared over ac. They told us that the speed was 23 meters per second. So 23 squared over that 2.63 I got will be my radius. So if I go ahead and I do 23 squared divided by that answer, I get 201.45. All right, fine, 201.5 meters for the radius. All right, and then lastly, they say, what's the speed of the car if the deflection was 9 degrees while rounding the same curve? So this time what they're saying is it's the same curve. That means it's the same radius, okay? So I know the radius. They want to know the speed. They didn't tell me AC, but they told me the deflection angle. So basically I'm going to say, okay, fine, be that way. Coming over from this, G tan theta is AC, right? And AC is V squared over R. They want to know the speed. So tan theta square root is the speed, right? And so here we go. So it's going to be the square root of 9.8 times that radius, 201.5. It's the same curve, same radius, times the tangent, and they told us the new angle is 9 degrees. So I take my calculator and I do 9.8 times that radius that I got in the last part times the tangent of 9, right? I take the square root of that, and my velocity is 17.7, rounds off, meters per second. Ta-da! And that's the answer to part C. All right. All righty. Good enough. That is problem 9. We have gone through problems 1 through 9 of that homework set. I think that's enough for right now. Perhaps I will show you problems. Let's see, problem 10. I'll just say a few words about. Problem 10, I'm not going to say much about right now. It's a trickier thing. The idea is that a plumb bob does not hang exactly along a line directed at the center of the Earth. Why? Because the Earth is rotating, and when you rotate, this will tend to look like it's spinning out. You know, want to swing outward a little bit. Does that kind of make sense? So if I were at the surface of the Earth, I'm going to represent the Earth as a sphere, okay, instead of an oblate spheroid, a squish sphere, which it really is. But that's okay. Right? Okay. And you say, hey, if I were standing at the equator, then all would be well. Okay. But if I'm standing up somewhere else, like, you know, here, right? And I'm holding a pendulum bob. I should have just drawn the pendulum bob, shouldn't I? Yeah, I should have. The point is, the center of the circle that I'm making is right here, right? I'm going around like this. I'm not going around like this, right? If this is the equator, you know what I'm saying? Yeah. Earth's axis goes like this. I know, compared to the plane of the ecliptic, this is tilted, what, 23 degrees or something? Don't sweat that. The point is, we just care that we're rotating around like this. The center of the circle is there. And that means that gravity wants to pull you towards the center of the Earth this way. So you would expect a pendulum bob. Here, look, here's a ceiling in my really tall house. You would expect the pendulum would hang right along the line. All right, pretend that's the center there, right? Yeah, it's a perspective picture, right? Right, you'd expect it would hang along that line, but because we're spinning, it's going to tend to swing outward a little. Can you picture that? And so it's actually going to hang off just a little bit, much smaller than I'm drawing it here. There's going to be a little angle here, okay? Because as it rotates, it will tend to want to swing outward a little. Does that kind of make sense? Because the ceiling and the house and the rest of this planet here, right? We're all accelerating this way. It's going to make it kind of swing out a little bit as we whip around in a circle. Okay, so that's it. So you're just trying to find, hey, what's that angle here? Now, if I were right here at the equator, right, in my ceiling in my house, and a pendulum, you're like, hey, it's trying to swing around. Gravity pulls it this way. It's trying to spin around. It needs to have a net acceleration inward. You see, this tension force isn't going to be as big as gravity, and they won't balance out. I'll have an acceleration inward. But the point is, it's right along the line, though. You know what I mean? Swinging outward just pushes it along that same line. So it actually will point toward the center of the Earth if you're at the equator, right? But if you deviate up here, it's not going to be right toward the center. Yeah. So that's the point. It's a tricky calculation to do. It's kind of tricky drawing the diagrams and such. I put them on that answer key. I kind of showed you the starting up diagrams and my final answer. You are welcome to attempt calculating it out and see what you think, all right, and see if your answer matches mine, but I'm not going to run through that now. All right, problems 11 through 14, you do want to look at these because problem 11 is a problem from an old AP exam. This is a free response from an old in the 80s AP exam. And this is a problem from another really old, I want to say it's 1984, AP exam. You want to go ahead and give these a shot. Okay, and this is a banked curve problem, which is something you want to be familiar with. Look, it was on the exam. You probably want to know it. Okay, and these are two more banked curve problems. We will talk about these in class next time, probably. That is it for this video.